I'm Robert Kleinberg, speaking to you from Cambridge, Massachusetts, sunny Cambridge, Massachusetts, actually. And as Evan said, I'm speaking about methane emissions from the fossil fuel industries of the Russian Federation. And yes, I've given a number of talks in the meta series in the past, but I've been working on this for more than a year. So it's not, it's fairly mature, at least in my mind at the moment. So I think it's ready for presentation to this very discriminating audience. Here's an outline of what I'm going to be talking about in the next half hour or so. I'm going to start with emission factor inventories, comparing the United States with the Russian Federation. I'm going to have more than a few words to say about satellites as sort of an alternative means of figuring out what's really going on in these countries. And then I'm going to end up with talking about the economics of methane abatement in these two countries. As Evan has mentioned, there is now a long paper, so perhaps overly long paper on this subject in Earth Archive number 3342. Okay, so let's get started. I think most of you know and probably very familiar with the emission factor method, which is the standard way of estimating methane emissions from various industry sectors, including the oil and gas sector. Just a quick reminder, the emission factor method depends on two sort of multipliers. One is called the emission factor, which is, for example, the estimated annual emission from a single device, perhaps as determined in the lab or an engineering calculation. And then that's multiplied by a so-called activity factor that is associated with the emission factor. And that is, for example, the number of those devices nationwide. So for each type of device or equipment type, you multiply those two things together, and then you sum up all the over all the devices and equipment types, and that gives you the annual emission in kilotons per year of methane. Now, I have to say that the Environmental Protection Agency, as it implements this, is unbelievably fastidious. So on the left is a spreadsheet from the latest greenhouse gas inventory, additional information. And what's going on here, each line is an equipment type. And this is just from the natural gas systems. The petroleum systems have another spreadsheet that looks very much like this. And then the columns are the amount of methane, the calculated amount of methane coming from that equipment type for each year from 1990 to the latest reporting year, which is, in this case, the year 2020. Each year, the EPA reconsiders all the emission factors and recalculates the entire series from 1990 to the present. So this is, again, it must be a labor of love because clearly a monumental amount of work goes into this. And I have to say that EPA is very transparent in how it calculates and changes its emission factors. It's really a model. And you wind up with lots and lots of numbers. In all, there's between the natural gas system shown here and the petroleum systems, there's 250 line items that EPA keeps track of. So again, a monumental effort. Okay, so what's the result of all this? This every year, the EPA, as you know, puts out its greenhouse gas inventory that is conveyed to the United Nations Framework Convention on Climate Change as its national inventory report, NIR. And so what I've done here is on the horizontal axis, I have date in years ranging from 1990, where this system sort of got started, up to the present. And then the vertical axis is the methane emissions, total national methane emissions from the oil and gas industry in kilotons. You're probably wondering why there's so much white space on this chart, and it'll become obvious in a minute why that is. But you can see that, as I've told you before, the U.S., according to the EPA, U.S. methane emissions has been declining steadily but slowly since 1990, a few tenths of a percent per year. And then every year, the emission factors are recalculated, so you get these different lines. The activity factors basically remain the same. So that's the situation with the United States. Okay, what about Russia? Well, Russia, not quite so meticulous in its record keeping. So instead of 250 line items, it has 14 line items, broken down into very, very large pieces. So the top 5 are from the gas sector. The remainder are from the oil sector. Again, methane emissions. So each one of these has an emission factor. And then the activity factor for the gas is the amount of gas produced by Russia. And for the oil, it's the amount of oil produced by Russia. So the activity factors are very simple and easy to trace. But that gives rise to some inevitable inaccuracies. So for example, to compute the methane emissions from, say, the main pipelines, line number 2, there's nothing about the length of the pipeline. It's all like, okay, the gross amount of gas produced by Russia, and there's a number, an emission factor that you multiply, and that's their supposed methane emission, but it doesn't take into account that various pipelines have various lengths and are running for various distances. So it's not a particularly careful method, but this is sort of ground level methane emissions and not nearly as meticulous, I would say, as US. Okay, and let's see what the results are for that system. Well, it's not quite as consistent as for the United States. So again, we have horizontal axis is years, and each report is shown in a different color. 2014, the 2014 report in blue, 2016 report in green, 2018, 2020. And you can see these are like all over the place. The activity factors basically are the same year after year. I mean, that's just national production, so that's kind of dead easy. But the emission factors change by very, very large amounts in these 14 categories, giving this sort of wild variation in the estimated methane emissions from the Russian oil and gas industry. So, what does that all mean? Now, there's a whole bunch of international agencies that also estimate methane emissions from Russia, and I talk about them in that big report on Earth Archive. But basically, you have to ask yourself, who would know more about methane emissions than the government of the Russian Federation itself? I mean, everybody else is making guesses that are even more like guesswork. So, that's why I sort of focused on the official reports to the UNFCCC on the theory that, well, presumably the Russians know what they're doing, and if they don't know, nobody knows. Okay, so let's just have a look at why those curves are changing so much. So again, here is the emission factors now shown in a table. Each column is a report year. So this is the report issued in 2014, covering 1990 to 2012, 2015, covering up to 2013, and so on. And so this is the gas sheet. And as you see, the activity factor is gigograms divided by 1 million in terms of meters cubed. And then there's that's the activity factor. And then here's all the emission factors. And what I've done here to sort of figure out what's going on is that every time the emission factor went up, I have a blue arrow. And whenever the emission factor goes down from the preceding report, there's a red arrow. And like I say, some of these changes are really, really big, like on order of magnitude size, which explains why those curves are bouncing around so much. In the rightmost column is the Intergovernmental Panel on Climate Change, IPCC, estimates of default emission factors from 2006, and the Russian numbers sort of bounce around those. They've been generally sort of getting closer to them. But this is what nations normally use if they don't have any better numbers. I will say that it is a tribute to the authors of the EPA and Gas Research Institute report that came out in the mid-90s. Principally, Matt Harrison was the principal author. That this method is still being used universally and by both the United States and Russia, although I must say with different levels of conscientiousness and care. So this is the gas spreadsheet. Same thing for the oil spreadsheet. And now it's, again, in terms of the amount of oil going through their entire system multiplied by these various factors. Okay, so where does this leave us? Well, let's compare what Russia has been reporting to what the United States has been reporting. So this is a chart of emission years since 2013. The report comes out 2 years later. And what I've done here is I'm on the vertical axis, I've plotted oil and gas methane intensity versus year. And for the intensity, what I've done is I've taken the methane emissions in terms of barrels of oil equivalent per day and divided by total production of petroleum liquids in barrels of oil equivalent per day, plus gas also in barrels of oil equivalent. So basically, this is an energy ratio. There are many ways of calculating methane intensity. People have different methods for different purposes. I kind of like the energy intensity myself, but for general purposes, but other ways give you very similar results in terms of relative differences between the US and Russia. So the big story here is that the USA intensity has been going down, mostly because the production of oil and gas has gone up so much over the years due to fracking. Russia, wow, this is impressive. Russia has reports that its methane intensity has decreased by 89% between 2013 and 2019, 6 years. In 6 years, their methane intensity has decreased by 89%. Honestly, I don't find this credible. Like I say, there aren't any better numbers out there, but I mean, does anyone really believe this? And the commercial implication of this is kind of profound, because if we're looking at a world where, for example, importing nations that import fossil fuels are going to be very curious about the upstream greenhouse gas impact of the fuels they're importing or the commodities they're importing that are being produced with these fuels, then it's going to be very important who has a lower greenhouse gas impact. And Russia has sort of put itself in a position of being the low emission provider. So are we really going to sit still for that? That's kind of a policy question out there. But I think eventually might be an important one. Of course, now with Ukraine, everything is mixed up and people aren't thinking about that at the moment. People are just scrambling for supply. But I think we can see in the future, as greenhouse gas emissions sort of come to the fore again, people are going to be looking at these numbers carefully. And these are the most authoritative numbers around. Okay, so immediately you're going to be thinking about, well, what about satellites? Because the Russians are not going to allow airplane flights over their oil and gas industry. I can tell you that, along with a whole bunch of other countries that are not interested in allowing measurements to be made over their production sites and so on. But satellites can go anywhere, look at anything, right? And satellites make two kinds of measurements. One is what I call top-down, and this is a sort of a purely an atmospheric measurement. And then the other kind is a plume measurement. We'll talk about that in a minute. Now, the top-down measurements, so you know about TROPOME and GOSAT, these are satellites that view the entire Earth every day. So they are great for checking up on everybody simultaneously. But they do have, and the people that, I just want to say at the outset, the people that have launched these satellites, engineer the satellites, and do the signal processing are amazing scientists. And I just have nothing but respect for them. But we need to understand what the limitations are. Very, very important to understand that. So the top-down measurement, basically what the satellite measures is the line integral of methane concentration from a pixel on the Earth up to the detector in orbit, typically 500 kilometers, which is great, except that these measurements really are not accessible where you have wet, snowy, cloudy, or mountainous terrain, or in the presence of limited and or low angle sunlight. Now, these are the exact conditions that are fairly common in the main Russian oil and gas producing regions, the Volga-Ural, Timon-Pokora, and the Western Siberian sedimentary basins. So Russia is a pretty problematic place to be making these satellite measurements. I'm just going to contrast that with a place like the Permian Basin in West Texas and New Mexico, where the skies are not cloudy all day. You don't have much snow. Terrain is generally flat. Ground is brown. That's kind of a good thing for satellites. They like brown earth. And so you get really, really excellent measurements there. Russia, not so much. Now, the other problem with this top-down measurement is the signal processing, which is basically based on a Bayesian algorithm, which is sort of the most modern and up-to-date way of dealing with this. And Bayesian processing requires initialization with what are called priors, which is an initialized guess. So you're putting in a guess, and then the machine is, turn the crank. And this is pretty problematic because what kind of guesses do you have? Well, the guesses that are most often used are, in fact, those inventories that come from the national inventory reports submitted to the UNFCCC. So, or what other more authoritative guess are you going to put in? So just to quote some papers that have come out, this is from a paper principally authored by Marielle Saunois back in 2016. In poorly observed regions, which is Russia, top-down inversions rely on the prior estimates, that's the initialized guesses, and bring little or no additional information. So where the satellite measurements aren't really, really good, what you're looking at mostly is your initial guess. And just a more recent comment from you et al., a recent paper in the Geoscience Model Development, improving the spatial accuracy of bottom-up methane emission estimates, that's the priors, is one key need for advancing top-down source assessments. So what you is saying is that in order to do a better job of getting data from satellites, you've got to have better bottom-up or inventory methods to put into your processing algorithm. So these are real limitations. And by the way, if you read these papers and you read them carefully, the people that write them are very, very conscientious about telling you the limitations. It's up to us to read those papers and understand those limitations, because the authors are being totally upfront but we need to make sure that we're reading what they write. Now, with respect to plume measurements, this is really a different world. The data is the same. It's still the line integral of methane concentrations along that path from the Earth up to the satellite. But the problem with the plume measurements is that although you see the whole Earth, the measurements have a fairly low sensitivity. So, for example, with tropomy, if you have a sensitivity of maybe 5, 10, 15 tons per hour, which is a gigantic leak, rarely seen, that only accounts for maybe 10% at most, I would say, of total methane emissions from the oil and gas sector. So, so these are measurements with low sensitivity, and you don't get everything. And the geographical constraints are the same as the top-down measurements. You're going to have problems in your cloudy, snowy areas. Another approach is used by GHGSat and others. MethaneSat and so on will approach this. But it's going to be higher sensitivity. That's good. But you're going to have to task the satellite to measure selected targets. So it's not really good for a global survey or a big country like Russia. Now, as GHGSat and others, sort of populate their constellations of satellites, they'll get more and more comprehensive, but that is still somewhat in the future. Okay. So let's just have another look at the satellite data, just to kind of follow up what I've told you. The latest sort of full Earth stuff is from tropomy, which is sort of best for kind of a wide range of conditions. That's been discussed in the literature. So here's, again, data from the paper by Sanois et al. And what I'm showing here is GOSAT data for 2017, and this is the whole Earth. This is global. And on the horizontal axis here are 11 different processing schemes for analyzing this data for the whole Earth. So these are done by different groups or groups doing things in various ways. And it gives us an idea of the consistency of the processing product. So here, when you're looking at the whole Earth and you're looking at total methane emissions, well, this is exactly what the satellite measures. You can hardly go wrong with it. And so the black dots at the top are very, very consistent. You're measuring all methane emissions, natural and anthropogenic, on the whole Earth. You get really consistent numbers. That's great. If you try breaking it down, you're going to start running into problems because there is nothing, I want to repeat this, there is nothing in the satellite data that distinguishes natural from anthropogenic sources. It's all methane. So there's no isotopic information. There's no ethane, at least not in these data. So you're going to have, a little bit more ambiguity, and you can see the anthropogenic emissions in blue, the natural emissions in green are pretty consistent, but not totally. Then the red data are from fossil fuel, which is a subset of anthropogenic. And again, with the whole Earth, you get, we know how much fossil fuel we're generating and so on. So you get fairly consistent data. But again, I would say more uncertainty. Now, that's the whole Earth. If you go to an individual country like Russia, even a big country, and Russia is big, the numbers become much, much more questionable. So if we're looking at total emissions out of Russia, again, using a single data set, everybody uses the same data, but 11 different processing methods, total methane emissions vary by about a factor of 2, depending on the kind of processing you use. And then if you want to segment that into anthropogenic in blue, natural in green, or fossil fuel part of anthropogenic in red, you can see that you really have fairly large changes in these estimates. And that's because you're using different priors. Again, the satellite isn't measuring these individual sectors individually. It's just really measuring the total, and the priors, your estimates that you put into the algorithm are really what's determining how these things get partitioned. So this is all pretty tricky. That's kind of the take-home message here. And again, the people doing this are extremely clever. And things are getting better, but we've got a ways to go. Okay, let's move on to abatement. Last topic. The International Energy Agency puts out methane abatement potential curves every year. Last one came out in February. Just let's look at the United States. IEA says that the United States oil and gas industry emits 13.8 million tons of methane a year. They get that basically by looking at all the papers that you people in the audience have written, and that's kind of their, to be honest, guesstimate based on the best data they see in the literature. Now, of that, so that's emissions to be remediated. So of that, IEA calculates that 2.5 million tons, or 18% of the total, can be remediated at negative net cost. In other words, you get more from selling the gas than it would cost to repair your problem. So 18% is a pretty low number by global standards. And what this tells me is something I already knew from my days at Exxon and Schlumberger, and nice to see people from those companies in the audience, which is that the U.S. oil industry does not like to leave money on the table. And if they can fix something and make more money, they will fix it. So they are pretty far along on that process, as shown here. IEA says that it's probably not possible to abate the entire 13.8 million tons, but we should be able to fix about 9.6 million tons, or about 70% of the total. Now, if you take these curves, these cost curves, and on the horizontal axis, we have cumulative abatement in kilotons of methane. Vertical axis is the annualized net cost in dollars per million BTU abated. A million BTU is 1,000 cubic feet, or about 30 cubic meters of gas. If you figure what you can sell the gas for, basically the annualized net cost of abatement is about $1.7 billion. Now, okay, $1.7 billion, that's real money. But considering that the US oil and gas industry makes about $300 billion a year, and its capital budget is around $100 billion a year, the 1.7 billion doesn't really look crushing. It's about 1.7%, 2% of the CapEx budget of the industry. So yeah, I think it's probably affordable. But of course, no one wants to spend money unless they have to. That's why it hasn't been done. That's why we need regulations. Here's Russia. Russia, not so good. According to IEA, 6.3 million tons, or about 44% of total Russian emissions from oil and gas industry, can be abated at negative net cost. So the Russians just aren't paying attention. That's all I've got to say. And to be honest, the 44% that can be abated at negative net cost is sort of typical globally. Hey, you have to pay attention to pay attention. So anyway, and again, the technical abatement potential, about 10 million tons, which cleans up 71% of their problem. Annual net cost of abatement, again, if you integrate these curves, which I have done for you, you come out with $78 million of profit. So the net cost is negative. That's a profit, which is chump change. I mean, in the oil and gas industry, But, hey, you can fix your problem and actually make money, at least a little money. So they should get on it. Okay, just for purposes of reference in your slide deck, all those colored boxes on the previous two charts had specific abatement references, and that's all shown here. You can look at that when this is all posted on the Meta website. So just to sum up, US EPA emission factor inventories are remarkably granular. We can be proud, our taxpayer dollars at work, and they are meticulously curated. I mean, wow. Russia, not so meticulous. Their emission factor inventories are pretty crude, 14 big categories, and subject to very large year-to-year variations, which have been all downhill lately. With a net of 89% reduction over 6 years. Not credible. Therefore, Russia now claims that its methane emission intensity is lower than that of the United States. But to be honest, the US inventory is also not very credible. It's much more careful, but let's face it, we all know that it's got some systematic problems. National methane emission inventories by satellites are hindered by fundamental limitations in both data collection and data processing. It remains a work in progress, and we do expect progress to continue. But certainly, no matter how good the satellites get, comprehensive measurements by other methods, such as aerial surveillance, ground-based, continuous monitoring, and so on, will also be required to really solve this problem. The IEA estimates that Russia can abate 70% of its methane emissions while improving its net revenue by $78 million. So again, not much money, but it's worth doing. And again, full story on Earth Archive. So with that, just wrap it up. I'm looking forward to questions and conversation. And those of you who wish to contact me, here's my email address. It's on the last slide in the slide packet. So again, thanks very much for your attention.